Hello, everyone. So what we're going to do today is we're going to continue on. So I'm going to share my screen, actually. Please ignore my super messy desktop. We're going to continue on with what we were talking about last week. So this was the basic picture that we need to have in our head whenever we're doing trigonometry. We definitely have SOHCAHTOA lurking around, but really the thing that I think is most important is that we remember that we can rotate triangles around, and so we've got a triangle like, I don't know, here's a triangle, and then it's a big triangle or whatever. But we can, with any triangle, so this has got 76 degrees, we can always rotate the triangle so that the 76 degrees, so that the 76 degrees, let's go this way, 76 degrees, so that it looks like that. So that we have the angle in the bottom left, and then we have the run and the rise. And this is true no matter what scale the triangle is, whether it's big or small, no matter what the angle is. If we think about it in terms of having the angle in the bottom left and the right angle over on the right-hand side when we're looking at a triangle, it'll make everything a lot easier for us. It lets us see what each of the components are doing. Sine tells us how tall the straight side is, and cos tells us how far across the base of the triangle is. And if you don't have the angle in the bottom left and the triangle in the bottom right, the right angle in the bottom right, then it's not going to be as clear when I say that tan theta is rise over run. The rise divided by the run. So with this picture in mind, we're going to see about, instead of finding sides, which is what we did last time, we're going to see about finding some angles. So I'm going to be flicking back to this picture. So, we're going to have different angles. But whenever we're trying to find an angle from side information, we're actually not going to know what this is. So I'm just going to quickly get rid of this. Haha, now we don't know what it is. Only I know what it is. But we're going to figure it out. Okay, so let's open up Mathspace. And the subtopic I'm going to be taking a look at today is finding unknown angles. I am looking in the New South Wales Maths Standard 2 textbook, but I am sure that you have a finding unknown angles subtopic somewhere in your Mathspace textbook. So let's do it. Let's just try one of these out and see what it's got in for us. So first of all, before we do any triangle business, we have to understand what is being asked of us when we have sine theta equals 0.2. Now, there is one extremely incorrect way to do this, and that's to go, well, if sine theta equals 0.2, then theta equals 0.2 over sine. And this is extremely wrong. But why? Why is it wrong? Well, Sine here is not a number. So we don't divide by sine. It'd be like saying, well, if x squared equals 9, then x is 9 divided by squared. Also wrong, because squared isn't a number. This sign here is a function. So we do something similar to dividing, but we have to divide in a function way. And what is it actually asking us first? Last time I showed you the picture of what sine looks like. This is the theta, and this is 1 and minus 1. And then I'm going to just draw this as 90. And I'm going to just briefly flick back to my applet here. So let's start off with theta, that's the green angle down here, being close to 0. And remember that sine theta is the height. So it starts off really, really small. So if theta is small, then sine theta is also small. And then as theta gets bigger, sine theta gets bigger as well until it gets to 1. Cos does the opposite. Cos starts big and ends small. Sine theta starts small, grows big. So let's draw sine theta in. Sine theta goes something like this. It's not, I'm doing it with a mouse, which is a bit less good, but it's got a kind of a curve to it, but it kind of goes like this. Last week, I also talked about how it keeps on going. It goes up and then down and around, but we're not going to talk about that today. So what we're asking here is sine theta is 0.2. So I know what the height is. So in this case, I say, well, sine theta equals 0.2. And what I want to do is I want to do the opposite of what I usually do when I do functions. Instead of going from the x-axis and finding the y value, I'm going from the y value and I'm trying to find the x value because I want to find theta. So if sine theta equals 0.2, I'm saying what angle gives me 0.2 when I plug it into sine. Okay. And remember before when I said that it's not true that we divide by sine? So I've got sine theta equals 0.2. Instead, this time, I'm going to write an equation which looks like this. Theta equals sine inverse of 0.2. Now, inverses can be a little tricky, but remember that to the power of -1 kind of means like a divide. So it's not 0.2 divided by sine. This to the -1 here is telling me that I'm going from the y-axis down to the x-axis rather than the regular way, which is going from the x-axis up to the y-axis. Now, I will mention that annoyingly, just like a lot of things in mathematics, there are other ways to write this without using the -1 power. I'm going to be using the -1 power today, but you may see a sine of 0.2. Maybe this is what you're familiar with working with, or even arcsine if you are in other parts of the world. And it's just annoying because people want to be different and stuff, but like these are all the same thing. So I'm going to be using this one. So how do I find sine to the -1 of 0.2? The answer is I am going to use a calculator. So I'm going to get out old mate Google, sine to the power -1 of 0.2, and we'll see what Google tells me. It doesn't work. Okay, let's try something else. Let's try a sine 0.2. And it's telling me in radians. That's not so good either. But your handheld calculator will probably have something like this in a devoted button of yours. And I'm pretty sure, whoops, wrong one. If I open up my GeoGebra, I can get my calculator out here. Let me just save this so I don't lose this. Triangle. Go into the apps section, I should have a CAS calculator. Well, I think a scientific calculator will be fine. Oh, cool. Great. It opened it up without messing it up. Okay. So this time, let me just go back to my problem that I was working on, because Google, what a fail. Thanks, Google. So you will have a calculator that lets you do this kind of thing. And I'm going to do sine of 0.2, but I'm actually instead going to do to the power -1. And it tells me that the answer is 11.53695 degrees. So I now can tell that I need it to the nearest degree. So that's 11.5. Just get out of this, 11.5. Oh, I'll actually answer the question correctly. It's 12, there we go. So what did we learn from this? If we ever have an expression that's sine theta equals something, then the way to find theta is to do the inverse. I'm just going to write that up quickly. I'll get a new color out. Sine theta equals box with a blah. Whatever this blah happens to be, then theta equals sine inverse of that blah. You can think of it as the inverse is the trig version of dividing both sides by sine. We're not actually dividing both sides by sine, but we are applying a different function. We're going from the y-axis down to the x-axis rather than from the x-axis across to the y-axis. And this works whether it's sine or it's cos or it's tan. So whenever we're finding so it's tan inverse and cos inverse as well. So whenever we are finding angles, what we really want is we want to get it so that it's sine theta, cos theta, or tan theta equals something. And then we're going to do the inverse to get the angle we're looking for on its own. And that's what these first few questions in this subtopic are focused on us doing. Okay, so with this question here, what we do is we do theta equals cos inverse of 0.73. Just put it into our calculator and get the answer out. Same thing here, tan inverse. Theta equals tan inverse of 1.3. Theta equals cos inverse of 4/9, and so on and so on. So all of these questions up the top will get you practice in doing sine inverse, cos inverse, and tan inverse. Okay, now let's get into slightly more interesting territory. Here, we are looking at a triangle, and we're not told whether we should use sine or cos or tan or what to do with it. I'm actually going to open this question up so we can have a go. So first of all, my triangle's up and over there, my angle's up and over there. So I'm going to get out my GeoGebra again. And I'm just going to make this a little bit smaller, get rid of all my business. Okay, so the right angle's kind of, yeah, let me just move this, make this a bit smaller so we can see. Okay, let me try and make these two the same. So the angle's kind of down here. Rotate like this. So I've got, it's up the top there. These over here. Let's rotate this a bit more. Oh, not quite there. Okay. Yeah, that's close enough. Oh, I did the minimizing thing. Rip. Where did it go? There it is. Okay. There we go. Close enough. So you can see from this that I've kind of messed up what I had originally. Like cos is no longer the horizontal, it's kind of slanted downwards, and sine's like this. But what I can tell is that I know this red side and this blue side. These are the two sides I've been given. You might have been taught it as saying, well, I know the side that is adjacent to the unknown angle, and I know the side that is opposite the unknown angle. But if we were to put this triangle back into a proper position, like we were to try and rotate it around, I can imagine it would look something like this. So the B would go over here somewhere, and I'm just going to rotate it a little bit more. Like that. So I think that would be close to what the triangle is after I've done rotating it. Just sort of imagine sticking a pin in there and rotating it around clockwise, and I get something that looks like this. I just need to match them up. And tan theta is rise over run, or alternatively, it's the opposite over the adjacent. I can see that I have the opposite side and the adjacent side. So I'm just going to write this equation in to Mathspace and see what it tells me. So tan, and I'm not going to write theta because the unknown angle already has a name, and its name is x. Okay, and then we equal the opposite side, 15, divided by 19. And what do we think of that? It's looking good. Now we are in exactly the situation I was talking about before, where we have tan of something equals blah. And if I get out my handy dandy calculator, instead of doing sine, I'm going to do tan. And instead of 0.2, I'm going to do 15 over 19. Tan inverse is the way that I move the tan over to the other side. And so this is telling me that if tan of x is 15 on 19, then, I'll just write it in like this, x is tan to the power minus 1 of this thing. And thank you, calculator. You've told me what the answer is, 38. So what was tricky about this question? Well, if I had told you at the beginning that this was the equation, then this part is easy. Well, it might not be easy, but once you've done enough practice on these questions at the top of the set, you'll be used to doing inverse tan or inverse sine or inverse cos. So the tricky part is actually to make to make this equation in the first place. The reason that I chose tan is because I knew the opposite side and I knew the adjacent side. I did tan of the thing I want to find is opposite divided by adjacent, and then I end up with x equals 38 once I do the regular tan inverse thing. Okay. So this time, when I look at this triangle, this is going to be exactly the same as the previous triangle. It's a little bit different, but not by much. So x opposite is 21 and adjacent is 7.6. The opposite over the adjacent. So I can, and you can do this for yourself from the Mathspace textbook, just pop open the solution and notice that we have, these are the hints that you would get from here. Tan x is the opposite over adjacent. The opposite side in this particular question is 21. The adjacent is 7.6. And because I know the opposite and the adjacent, I use tan. So let's find one that doesn't use tan. Let's look at this one. Try it out. All right. So in this question here, I now have some different sides. And if I were to label each of these sides, this is the adjacent side. This is x, the thing I want to find. This is the opposite side. And this is the hypotenuse over here. So I can now see what I need, the opposite and the hypotenuse. If I open up my thing here, which ratio has opposite and hypotenuse? Sine does. Similarly to like we did last week, we could say that 12 is k sine theta, and we can tell that k in our picture is 13 and rearrange that equation. But we went beyond this and now we're just using SOHCAHTOA. And if you can figure out what you've been given, then you can just pick the right ratio and write the correct equation. And it's always a good idea to just check. Let's just check that we've got the right equation. Opposite hypotenuse. So I'm going to write sine x equals 12 on 13. Sine is the opposite, 12 over hypotenuse 13. We're on the right track. And then to find the answer we need, well, this time we're going, oh, I'll write it in Mathspace first. Sine to the -1 of this. Just check with Mathspace that we're doing the right thing. Still doing the right thing, okay. And that's exactly what we are going to put into our calculator. Sine to the -1 of 12 over 13, 67 degrees. 67, enter. Excellent. Okay. The big difference between finding unknown sides and finding unknown angles is that we have to use that inverse sine, inverse cos, inverse tan at each step. And what we're going to do now is we are going to see a few applications. Now, let's take a look at this one. Let's do this. Even though this question is about a ladder, you can see that if you are ever involved in any sort of construction and engineering, or even if you're involved in design and graphic design, or anything where you need to know some precise values, you're going to end up using trigonometry at some level. What this angle is might be really important. It might not be so important if you're just grabbing a ladder and slapping it up against a wall, but it could be important if this was part of a structure. You needed to make sure that the forces on the building were okay for making it safe from an earthquake, or it might be something completely different, that you need to know this angle because it's going to be something that you reproduce a lot of different places. But what we do know in this setup is that the ladder is 1.51 meters long and it's 0.95 meters away from the wall. Now, this diagram doesn't even have the angle on it. Where does the angle come from? Well, this angle here, y, is down here. And that's because it tells me that the ladder makes an angle of y with the ground. So between the ladder and the ground is y degrees. Now that I've added that y degrees to the diagram, I can redraw the triangle because it's all busy. I don't need bricks and ladders and whatever. So I'm actually going to get my pen for this one so I don't make a complete mess of it. Oh. So I know that this is y down the bottom here, my angle. I'm going to make it green because I can. And then I'm going to put the other pieces of information I've been given. 0.95 here and 1.51 here. Once again, all of the work that we're doing here, the hardest part is just coming up with the equation. So once again, labeling the sides of this triangle, this is my right angle. So this is definitely the hypotenuse. Opposite the angle that I care about is O, and next to the angle I care about is A. So I've got this angle, and I've got these two sides, A and H. A and H, what joins adjacent and hypotenuse together? Let's just go back and check. Cos theta joins adjacent and hypotenuse together. So I can now write the equation cos the angle I want to find, y, equals the adjacent 0.95 divided by the hypotenuse 1.51. Now, I cannot stress enough that the hardest part of doing anything in this area is making the equation. Once you've made the equation, oh, it's just slap it in your calculator and you get the answer. It's redrawing the diagram, figuring out where y is, figuring out how these values transfer across to our new diagram, identifying which is A and H and O, and having identified that, figuring out what trigonometric function to use. And all of that work happens before we write this equation. So each of those steps are important and each of those steps are tricky. My advice is to always redraw everything. Even if the diagram is right there on your page, draw another one and slowly add the information in. Once you have a right-angled triangle with 3 pieces of information, 2 side lengths and an angle, you can then form the equation and move on from there. Okay, so that's finding unknown angles and unknown sides. The one thing I'm going to look at next is I'm going to look at what is called the sine rule. I'm going to skip degrees and minutes. Only New South Wales people do it. I know at least one person isn't from New South Wales, and degrees and minutes, I mean, the last people who cared about degrees and minutes were sailors, and they all got scurvy anyway. So we're going to just skip ahead. If you're in New South Wales, you can learn about degrees and minutes, but I want to make sure that everyone can benefit from this session. So today we're going to spend the rest of our session talking about the sine rule. Just wait for it to load up. Okay, so let's do what everyone always does. Oh, there's a thing. Let's click on it. Cool. Let's see what this does. I'm going to zoom in a bit so we can see a bit more. All sorts of things in trigonometry end up being kind of spooky in a lot of ways. And something that is true of triangles is that if you take the side length, in this case, I'm looking at the side length A, and divide it by sine of the angle that's opposite it, what do we get in this instance? Well, this is 4, and sine of 53.13, apparently that's 0.8. I'm just going to have to trust the applet on this one. B is 3, and sine of the angle across from it is 36.87. It's meant to be 0.6. You know what? I don't trust this applet. Let's actually make sure that this is true. Let's do it. Let's do sine of the angle 36.87. Oh, okay. Should have trusted the applet. So I get B is 3, and sine of this angle opposite it is 0.6. And C, the side length here, is 5. And sine of 90, well, that one I don't have to trust. I just know that sine of 90 is 1. So 4 divided by 0.8, let's see what that is. Again, we're not trusting this applet here. It's 5, okay. What about 3 divided by 0.6? 5. 5 divided, okay, I'm going to trust them on 5 divided by 1. So that's kind of funny that each of these ratios comes out to the same value. But the very, very interesting thing is that this is true no matter what angle size you have. So notice that as I'm moving this, what is changing and what isn't changing? So I can tell that A is not changing. A is not changing because A is staying at 4. I'm just rotating this capital A around. So this length isn't changing. So you can see that that stays at 4. But because I'm moving A around this point A, then this also isn't changing. It's staying at 3. So this numerator is staying there. But everything else is changing. All 3 angles are changing. And because all 3 angles are changing, the sine of those angles is also changing. But no matter what I do, no matter what kind of triangle I look at, whether it's a right-angled triangle or not, this ratio always comes out at the same value. this particular property is called the sine rule. And it says that if you take the side lengths, A, B, and C, and divide them by the sine of the angle, all of these are the same. It doesn't work for cos. It doesn't work for tan. It only works for sine, and that's why it's called the sine rule. If it worked for tan, it'd be called the tan rule, but it just works for sine. It can be a little bit tricky to see why this is true, but we can turn all of those fractions upside down as well. So a good way to think about why this is true might be that if I write something like 1 over 2 equals 2 over 4, a half is the same as 2 quarters. Well, I can actually flip these equations upside down. 2 over 1 equals 4 over 2. And that's still true as well. And 2 over 4 is the same as 3 over 6. And 2 divided by 1, that's 2. 4 divided by 2, also 2. And 6 divided by 3. So all I've done to get from that form to that form is I've just flipped everything upside down. It can be confusing sometimes, like you just say, oh yeah, you can flip them upside down, no problem. And you're like, well, I can't flip them upside down sometimes. The important part here is that we are taking everything and flipping every part of it upside down. So it's either this formulation here up the top, where the signs are all at the top, or this one here, where the signs are all on the bottom. Okay, well, big whoop, so what? Let's explore why this is interesting. Let's take a look at this triangle. Oh, where's my mouse gone? There it is. This triangle here. I'm going to just make a quick note. I'm just going to switch across to a blank page. This will do for a blank page. Okay. If we have one side and one angle that we know, if we know one side and one angle, and we want another side, that was our lesson last week, then we use SOHCAHTOA. That was last week. This week, if we know two sides and we want one angle, then we use SOHCAHTOA. And in this case, we're going to have to deal with the inverse function. But the cool thing about the sine rule is that if we have two angles and one side, we can find one side using the sine rule. But the super duper important part is that this up here is right angles only. Everything we looked at last week and earlier this morning was all about right-angled triangles. The sine rule is going to let us go from two angles and one side to find one side, but it's also going to let us go from two sides and one angle to find one angle. Sine rule. And this is any triangle. So how do you know that you need to use the sine rule? You are looking at a triangle and it's not a right angled triangle. And you can see on the triangle either two angles in one side or two sides in one angle, and you need to find the missing part of that for two pairs. Two angles, two sides, two angles, two sides. In any triangle, use the sine rule and you'll be able to find the missing part. Okay, so let's go back to this question here. This is a nice worked example. And I'm just going to get my pen out here. So we're in a situation where, first of all, I can tell that this is not a right angled triangle. It looks all wonky. So we can't use SOHCAHTOA. SOHCAHTOA needs a hypotenuse, and there's no hypotenuse here. So instead, what we do is we do what this picture down here is telling us to do. I've got this angle, and this angle is matched with this side. And this angle is matched with this side. It was exactly the same when we were playing around with that applet just above. And we're told that that's the side that we want to find, PQ, opposite over there. So how do we find this out? Well, the length of PQ over the sine of the angle opposite, sine 48, is equal to the same ratio in the pairing here. And that's equal to, I'm going to get my red out, 18.3, the length that we do know, divided by sine of this one, sine 27. Notice here that I've got my two angles that I know, my side that I know, and I want to find that side that I don't know yet. If I rearrange this, I'll be able to find PQ. And some wonderful Mathspace content person has already done this for me. Here's my equation. Then I can take this and remember all the way back to our first lesson. Equations are going to take us a long way. If I want PQ on its own and it's being divided by sine 48, I want to multiply both sides by sine 48. And then I get the much easier to work with equation that looks like this. And as soon as we're in a situation in which we've got the thing that we want equals something we can throw into a calculator, we throw it straight into the calculator. Okay. So let's now take a look at finding an angle using the sine rule. We're doing exactly the same thing as we did before. Suppose we know the side lengths A and B and the angle B, and we want to find the angle A. So my first question, oh, I've already scrolled too far, I've given the answer away. My first question was going to be, what angle can we find? And anyway, I'll notice what's happened here. This side length has been matched with this angle size. They form a pair. And these two form a pair as well. In this case, we could write 28. I'm just going to make a different color. Let's go with blue, sure. I could write 28 on sine of angle R, 28 on sine R, equals 41 on sine 39. That'd be using the equation in exactly the same way as I used it before. But I'm going to instead do the same trick that I mentioned, where I flip both of them upside down. And I do this because otherwise it's going to take a lot of rearranging to get R on its own. Not only is R inside a sine, but it's also in a denominator. So I'm just going to flip it over on 28, on 41, and then just get rid of this. There we go. I flipped it upside down. So at the very least now, the thing that I'm looking for, this R, is on the numerator and not the denominator. And that's what's happened over here. Okay, where to from here? First of all, we get sine R on its own by multiplying both sides by 28. And then, going back to what we were looking at the beginning of the lesson, we have sine of R equals something. This is definitely a big blah. Well, R is sine inverse of that blah. And we do sine inverse of this, put it into our calculator, and get our answer. Okay, so let's take a look at doing some questions. I got enough time for, let's go ahead and just do a tricky one. I think the best thing, as always, when it comes to anything that we're working on in Mathspace, hopefully you've had enough practice to take a look at some of the easier ones, and you can always rewatch the recordings. And so I'm now going to just jump straight in and do this one of the harder ones. Okay. So just like before, I can match them up. This side matches with this angle, and this side, I'm in a new color for that one. So we've got the side here matching with the opposite angle over there. And we have this side matching with this angle over here. And now we can write the ratio that we're interested in. So we're trying to find a side here. And that means that we want to write the side on the top. A over sine of the opposite angle, sine 40, equals this side over sine of its opposite angle, 83 over sine of 95. We can then multiply both sides by sine 40. Go from there. So let's just check it out. A over sine 40 equals 83 over sine 95. Looking good. We take this sine 40 and cut it out, and then we put it over here instead. Multiplying both sides by sine 40 to get A on its own. And that looks like something that we can throw into our calculator. Get our calculator out. I'll say the same thing that I said last week, which is always check that your calculator is in degrees. That's why I like GeoGebra's calculator. I didn't have to use it when I was doing things like powers or very basic stuff, but GeoGebra starts in degrees, and you're not going to get those funny answers with radians. So we'll just put it in. It is, I hope that one day in your long life, you will discover the joy of radians, but it is not this day. And the answer is 53.555. We've got to round that to 2 decimal places. It looks like 53.56 is our answer. 53.56, go. Awesome. Okay, I think we got time for just one more. This time, I'll see if there's one where they find an angle. Ah, it's in this one. It's in this set. Applications of the sine rule. That previous set will just get you practice with making the sine rule work. And the application set is when we're going to see if we can find one where we find an angle. The only difference when we're finding an angle is that we have to do that inverse sine at the end. Which ones of these look good? I want to find one where I actually have to find the angle. Okay. Let's do this one. Approximately 6 minutes, Mathspace. Okay, I've got 4. Let's see if we can do this. So here we have a triangle, and the first question we are being asked is to find the value of this angle. Okay, so I'm going to get my sketch pad out. This side matches with this angle, and this side matches with this angle. And I know I need to use the sine rule because I know 2 sides, I know 1 angle, and I'm trying to find a 3rd angle. 2 pairs, a pair of sides and a pair of angles. Pair of sides, pair of angles, that means you've got to use the sine rule. Okay. So let's write the equation up first. Because I am looking at finding this angle called B, I'm going to put sine of B on the top and the matching side on the bottom. And that equals sine of 64 divided by the matching side. And in the interest of time, I'm just going to cheat. I'm going to get Mathspace to tell me the answer. Well, I'll walk you through it at least. I multiply both sides by 7, and then I do inverse sine to move the sine across to the other side. And then this is something that I can type into my calculator, and my answer is 21.72. Okay, so let's go back up to the top and put that in. Where's this? I now know that this is 21.72. That angle there. Now the next question is going to ask me for this angle here. I can't use the sine rule, but what I can do is use the fact that these angles are always going to add up to 180 degrees because it's a triangle. That's true no matter what kind of triangle you are. So if I have 180 degrees and take away these 2 angles, I'll find the answer for this one up here. Okay, so let's do that. 180 minus 64 minus 21.72. And its subtraction, I'm going to use Mathspace, my calculator here. If you do this yourself, you're not going to get credit. But, you know, I work at Mathspace. I'm allowed to just do that. But now that we know that the angle here is 94.28 degrees, let me get rid of that question mark. 94.28 degrees, I can actually figure out what this distance is using the exact same trick that I did before. I've got an angle that I know and a side that I don't know, but I have a pair of matching angle sides, and I'm going to do the same thing. So this angle matches with this side in the same way that this side matches with this angle. So we're just using the sine rule twice. The first time we used it, we found this angle. We used the angle sum of a triangle to find this angle, and then we're going to use it one final time to find the length of this side. Okay, so let's put it in. This is the value C that we're trying to find. This question mark is C. It tells us that it's C in the question. C divided by sine of the angle opposite, 94.28, equals. We're going to pick this. You could definitely pick this one. Either of them will work. Remember back to our applet. That's too far away now. All three of those ratios were always the same. I'm just picking this one because it's going to be less time to enter because it's not a decimal. The side that we know here is 17. It goes on the top. And then sine of the angle at the bottom. Cool. Then I can just control X to move that denominator over to be the numerator over here. And then we can put that into a calculator and round it to one decimal place. I went a bit overtime today. Next week, I'm going to start on a new topic. I forget at this moment what it is. Let me figure out. I know it's up here. Oh, here we go. So what am I doing next week? Yes. Next week, we start bivariate data analysis. And as I said at the time, bivariate data analysis is a cool thing to say. What are you studying? I'm studying bivariate data analysis. No worries. Yeah. So tune in next week for bivariate data analysis. We're going to take a look at the kinds of stuff that statisticians do when they are looking for patterns in real data. Thanks for everyone for joining. Don't forget that the recordings are up at mathspace.co/au/academy, and I will see you then.